Okay, so now we all know what E is and natural logs are. Let's introduce the Arrhenius rate equation. So just to give us a bit of background here, rate varies with concentration. We've got a handle on that. Now, what about rate with temperature? How does rate vary with temperature? Just to kind of illustrate this, let's imagine I've got a rate equation. Rate equals K times the concentration of A, concentration of B. And I do an experiment where the concentration of A and B are both 1. And I measure the rate at 25 degrees, and the rate is 2 times 10 to the minus 4. Right? Okay. Then I do the experiment again. I keep the concentration of A and B both 1, but I raise the temperature to 35 degrees. Of course, the rate is going to go up. What has changed in my rate equation? K. Must be K. A and B haven't changed, and the rate has gone up. Maths says if this goes up, something on this side must go up, and if A and B are still the same, it must be K. So K goes up with temperature. You might remember earlier on when we introduced the rate constant, it's constant at a given temperature, a bit like Kc. K is constant for a given reaction at a given temperature. If we change the temperature, we change K. Can we draw another graph? Yay, another graph. I think we did this one the other day, didn't we? Might have even been yesterday. What's the relationship between temperature and K, which is the same as the relationship between temperature and rate, because rate and K go up in the same proportion. I'm confusing things. I'm going to shut up now. Draw a graph of temperature against rate constant. Say that again, Matthew?
Exponential.
Yeah, it's an exponential graph. So it should not go through the origin. So I've deliberately kind of stuck it back through the y-axis there to demonstrate that it doesn't go through the origin. And it gets steeper and steeper and steeper and steeper. Exponential graphs became very familiar to us all when 4 years ago COVID hit the country. So yeah, that was, yeah.
And they also intercept the y-axis of the y.
Well, that would depend on the graph, wouldn't it? Because we've got constants and things, stuff going on. But I'm sure you know more about it than me, Eddie. Okay, so we've introduced that idea of E. E is the exponential or Euler's number, and it equals that, which isn't that important. I've just said it's a special number. Oh, somebody who understands maths. What we need to know about is the Arrhenius equation. Now, the Arrhenius equation is going to be given to you in the exam. So that's a bit of a lifesaver there. Sorry, there's a constant. So the Arrhenius equation is K equals a constant A, and then e to the power of minus EA over RT. All of that, it's not really clear on the board there, but all of that minus EA to the over RT bit is raised, is the power that E is raised to. E to the power of minus EA over RT. So, yeah, fortunately, you will be given the Arrhenius equation in the exam. You don't need to learn it. But we need to know how to use it. So, let's just run through the bits and pieces that make up.
So, is EA activation energy?
Let's look at the bits that make up the Arrhenius rate equation. So, yes, EA is the activation energy. Note, put a big red circle around. It's measured in joules per mole. All our delta H's were in kilojoules per mole. Why are we suddenly using joules per mole? What are we using here? Units wise? Who uses joules rather than kilojoules all the time? Hey? Physics, very good. So what kind of units are we using here?
Standard.
Standard units, SI units, exactly right. So the gas constant R, you've met before. It was in the ideal gas equation, PV equals nRT. Again, it'll be given to you in the exam. You're not expected to remember the value of any constants. So 8.31 for that. Temperature, again, is in Kelvin, because we're using SI units. And A is a constant. It's just a numerical constant. It's usually a fairly large number. You can think of it as the frequency of collisions. That's a simple way of thinking about it. Okay. Should we try and put some numbers into this thing? See how far we get. In a reaction where the activation energy is 50 kilojoules per mole, how much does K increase by if you increase the temperature by 10 degrees? We'll assume that the Arrhenius constant A remains the same, which it pretty much does. It'll go up by about 1% for a 10-degree shift. Value of the gas constant is 8.31. How much does K increase by for a 10-degree shift in temperature? Can I leave you some time to think about that? It's not an easy question. You're going to have to use your Arrhenius rate equation. Forget about A. You don't need to worry about A. But you need to work out E to the minus EA over RT at 293 Kelvin and at 303 Kelvin. I'll leave you to think about that for a minute. I said it'd get dicey at about 15:15, didn't I? At 293 Kelvin, K is E to the minus 50,000 over 293 times 831, which is 1.21 times 10 to the minus 9. And then when we substitute 303 in there, we get 2.38 times 10 to the minus 9. If I look at how much that's increased by, from 121 to 238 as a ratio, well, it's almost doubled, that's pretty spot on. So the Arrhenius equation predicts that rate will roughly double for a 10-degree increase in temperature. In fact, it's slightly more than that, because we'll get an increase in collision frequency as well. But actually, the collision frequency is probably changed that 9.7 to a 9.8. It's a very, very small increase in collision frequency, that A factor. It's far more to do with the increase in well, you tell me. Why does the rate go up so much? It's not an increase in collision frequency. What is it an increase in? This is on the exam as well. That's it. Many more particles have energy greater than or equal to the activation energy. That's the difference there, isn't it? Okay. Right. I am not going to do that now. That seems cruel in the extreme. You worked very hard today. I'm going to give out your topic books.